This is a video on U substitution. So I got a few examples prepared, as you can see. Just a quick reminder of our power rule for integration. Take your exponent, increase it by 1, so we get x to the third, and divide your coefficient, 5, by that exponent, 3. So the first chunk there is 5/3 x to the third. Second piece, increase the exponent by 1, divide your coefficient, and you get 4x squared. Don't forget your constant of integration if this is an indefinite integral with no bounds. Now, jumping in difficulty here, we have a very complicated looking function that we're trying to integrate. We could raise this to the fourth, multiply by the 9x squared plus 9, and multiply by 5, or we could try U substitution. So we kind of have a little bit of a chain rule look here. The derivative of the inside piece is kind of staring us in the face right here. The derivative of 3x cubed plus 9x is 9x squared plus 9. So I'm going to take the inside piece here and call that U. Hopefully this is going to simplify things down a little bit. I'm not going to use the exponent here. So starting off, what I've done is just said, all right, this is U to the fourth. Now, hopefully, it works out really well that everything that I have left here is going to be a way, we're going to be able to write that in terms of du. So that means I'm going to find the derivative of u, and I get 9x squared plus 9 dx. So it's going to be this whole piece right here is going to be du. So I have 5 u to the fourth du in an integral. I'm going to take that 5 out, and have 5 times the indefinite integral of u to the fourth du. I can take the antiderivative of u to the fourth and get 1/5 u to the fifth. And when I multiply by 5, I just get u to the fifth plus c. And again, I can go back and plug my u back in. So I'm going to get 3x to the third plus 9x to the fifth plus c. If I take the derivative of that, I will get all of this. Let's try it for the next example. Sometimes the u is not as obvious. So what I'm looking for is something that has a derivative in here. So I know that the sine of 5x would have a derivative. I'd have to use chain rule, but I could do u equals the sine of 5x. The derivative of u would be cosine 5x times 5. So if I just start rewriting this, 10u cosine 5x dx, and I have most of this right here, right? I just have I need a 5, but I have a 10. So I'm going to factor that out. I'm going to say 2 times 5 times u times cosine of 5x dx. And now all of a sudden, here's my du. So I'm going to take the 2 out. I'm going to have u du. I'm going to integrate. I'm going to have 2 times 1/2 u squared. So I just get u squared. U was sine of 5x. So there's my answer. And if I did the derivative, I'm going to do 2 sine 5x times the derivative of sine of 5x, which is cosine 5x, times the derivative of 5x, which is times 5. And guess what? Same as the original function. All right, last one. Sometimes it just takes a leap of faith. So I'm looking inside. That's a terrible looking square root. Inside the square root is probably going to be my u. Find my derivative. I get 4x minus 4. Now you can see that that is not exactly what I need. However, if I manipulate this the right way, I can make this work. So I have the square root of u. I'm going to factor out a 3 from my 6x minus 6 to get 2x minus 2. I've not changed that. And what I'm going to do is I'm going to add in the number 1. I'm multiplying this by 2 over 2, which is 1. I'm allowed to do that. Now, I really need this to be 4x minus 4. So I'm going to choose to use the numerator. That 2 from the numerator is going to go multiply those in. And the 3 is going to join the denominator. So I'm going to rewrite it as this. 3 halves times 4x minus 4. And then I can pull that 3 halves outside the integral. So 3 over 2, definite integral. Now I have my u. Sorry, du. du over the square root of u. Which is really u to the negative 1/2 du. So now I can integrate using my power rule, go up by 1, multiply by 2, and multiply by my 3 halves, and I get 3 times my u to the half. U sub